Thank you very much. So Thompson couldn't make it here because of visa, but he really wanted to be here and he really did everything he could. We did not really want to take any chances on Zoom presentation or pre-recorded video, as we heard and saw yesterday. Lots of things suggested that we shouldn't. However, he's on Zoom for Q&A later, so I hope it's going to be a good discussion. So Thompson's work is about representation of materials that exhibit a lot of subsurface scattering, so which are most natural materials that we can see. And it's really hard to trick an observer to believe it's a photorealism with subsurface scattering, because people are really trained on see this sort of effects when different parts of the object surface interact in terms of light propagation. So we would really need to track light path underneath the surface for correct representation. And Monte Carlo path tracing is the reference, is the ground truth method to represent them on a computer screen with rendering. However, we know it's a very slow method and computationally expensive method. And also we have a lot of high frequency noise, which even tends to trick lots of denoising algorithms. So, yes, even if we try to denoise with some algorithms, so we can see it's mixing in. So we need really a different way to represent subsurface scattering. And a lot of work has been done on it. So usually we try to represent the material with a bidirectional subsurface scattering distribution function. And there's a bunch of methods on this. The most popular ones maybe are diffusion-based methods, and then the texture-based approximation, some pre-computational methods, and neural methods. We're going to be comparing to some of them the results of Thompson's work. And one of Thompson's previous works were on neural methods, so we are going to be comparing to this one as well. So about the diffusion-based model, they are based on diffusion theory, and the maybe first method was the dipole approximation, and there were others, which are the better dipole, quantized diffusion, photon beam diffusion, and directional dipole. So the base of these methods is approximating a material with an infinite layer, and we can have a point of light exit that we would like to receive our radiance for, and we would like to sample neighboring points on the surface in order to correctly approximate. So one of the most, apart from this simplification, we also say that for diffusion methods, we assume that scattering is quite high and absorption is low, which means we have a really low free path. So boundary conditions can be difficult to model accurately, and these methods are not really approximating heterogeneous materials well, because we assume infinite space. Some texture-based approximations are based on the diffusion approximation, so they are limited just as much as the diffusion approximation, and they cannot represent parallax effects, as will be compared later. Is important for subsurface scattering. There are some pre-computational methods, which is polygonal radiosity, which approximates every polygon with a transfer matrix. So they are as accurate and as good as the size of the transport matrix. And pre-computed radiance transport approximates with spherical harmonics the light transport. There were some neural methods as well. The first one was trained on a geometry. It was modeled on sign distance fields for local geometry. And radiance predictor neural networks, multiple layer perception presentation, and nerves. For the nerves, they have to be reliable. But those nerves who are currently reliable, they are based on BRDF, not on BSSDF. So what Thomson proposed is that instead of a planar surface, which is an infinite layer, we will think in a geometry space. So for each point of light exit that we would like to calculate our color in, we will sample our geometry with several input points. So for each of the points, we will calculate light transport, and then this will, if we have a sufficient amount of points, we will learn light exit direction and radiance as a function of number of points that we sampled on the geometry. So we will use Monte Carlo path tracing to generate these data points, but what Thomson also found during his work, that he actually doesn't have to fully train his model before rendering, so he actually trains it on unconverged data. We will explain later. So when we calculate outgoing radiance, we do light transport, we solve light transport equation. So there is this BSSDF function that is describing how much radiance compared to incoming flux is outgoing. And then during the rendering, we're basically solving the rendering equation. But how does it look in perspective of Thomson's approximation? So as we sample several points of incoming for the incoming light, then we will have a scattering operator that will act based on where on the geometry we would like to calculate our outgoing radiation and how many points we use to sample incoming light. So then multiplication by VSSDF will be replaced by scattering operator, element-wise multiplied with incoming radiance in the integral. So this method is bound to geometry, so we train on material but also on the particular geometry. His method can also work on a planar half-space assumption, just like before. So this will be then, if we train it on this, then we can also represent material in general and apply it on different geometries. We will compare to this a bit later, and we will see that training on geometry will be still a bit better. So when we train on the full geometry, we can still represent the full heterogeneous light transport. However, it is fixed to the underlying geometry. We will have to train for each geometry separately, although we don't need to do it on a fully converged samples. And this planar half-space approximation will be still limited to homogeneous light transport, but can be used with arbitrary geometry. This is the architecture of a multiple layer perception model that Thomson used in his work. So as input, it's an outgoing direction and outgoing point on the geometry, on the surface, and for each point of incoming light, radiance, direction, and the position. And the output is a scattering operator for RG and B. So here, Thomson compares two models. MEAT is a scanned model, and Kendall is a digitally modeled one. So he compares it to representation of object with differentiable rendering, and his previous work where he first proposed a neural subsurface scattering. This slide presents the ablation study in terms of what is the optimal number of points where we scan, the incoming radiance and direction and the position. So n in the model, number n. So he found that the best is to train it on 16 incoming points for one outgoing direction. He also compares to his previous work. So since the main advantage is since he found out that we don't need to have fully converged Monte Carlo path trace samples to train. So this resulted in some spare time that we have, 2 orders of magnitude. He compares it for different models. And also for the planar half-space representation, he compares the performance of his BSSDF plots. For materials, apple and potato, he compares his results to the dipole method, beta dipole, photon beam, directional dipole, and his model based on half-space representation and full geometry, as we described earlier. So 1 order of magnitude improvement in flip error for the full geometry method. Here's also, he found out that if we have 20 seconds for Monte Carlo path tracing and 20 seconds his method tracing, how would the noise result look like? So here is an order of magnitude flip error improvement compared to 20 second Monte Carlo path trace denoised. For the importance sampling, he implemented previous work, which is a nonlinear independent component analysis and neural importance sampling by Thomas Müller. For base distribution, he uses spherical Gaussian. Here's the importance sampling implemented by Thomson on the right side compared to uniform sampling. Here's the Mandarin model, the rendered result with or without importance sampling. I think impressive. And just as a last slide, he demonstrates how does his model is implemented in a standard rendering process. So just in the beginning, he says that the model isn't trained, or geometry is not trained yet. And in this case, he traces, during this, he traces on the Monte Carlo path tracing until the error, or loss function, is 10 to the minus 3. When we expect the error to go below 10 to the minus 3, we stop rendering with Monte Carlo, stop training, and we continue with model representation. Now I will put Thomson through for Q&A, and I hope it's going to be a good discussion between you.